Good afternoon, everyone.
Good afternoon, ma'am.
How are you all doing? How are you all
Good,
doing?
ma'am.
How's the practice going on?
Nice, ma'am.
You're able to solve the questions?
Yes, ma'am.
What about rest of you guys? Okay. Let's just see 2 more minutes. Let's see if Avni joins. I think 2 more people are there, right? Any doubt in the rules, understanding of the IUPAC rules? It is all clear?
Yes, ma'am.
So the 2 questions are on the board right now. Quickly do them until all of you are joining in. Until then, don't waste your time. The 2 questions are there, 5th and the 6th one. Tell me the right answer for each one of them.
Ma'am, done.
Done. Let's see what our others are up to. Good afternoon, Sheetal. Good afternoon, Shanuka as well. Are you also done with the answer? The 5th and the 6th one on the board? Good afternoon, Pushkin. Okay, Ankit, tell me the answer for the 5th one.
3 bromo, 1 chlorocyclohexene.
So that would be option number 3, right?
Yes, ma'am.
And even Sheetal and Shanuka is saying option 3, even Reshma is saying 3. So everybody is clear how is the numbering done? So the double bond will get the first priority. 1, 2, 3, 4, 5, 6. So that means it becomes 3 bromo, 1 chlorocyclohexene. What about the 6th one?
3 times 4 for dimethyl heptane.
Okay, so you are saying 4th one, right? Sheetal is also saying 4th one. What about the rest of you guys? So what is it actually? How have you numbered it? You have numbered it from here. 1, 2, 3, 4, 5, 6, 7. So 4, 4 dimethyl it is, yes. 3rd ethyl it is, and it is 7 heptane. Perfect. Can you see question number 7 over here? So 7 has a double bond followed by the bromo group. How will I number it and name it? Option 2.
4 bromo, 3 methyl pentene.
4 bromo, 3 methyl pentene. Okay, so Ankit is saying 1 and Shanuri is saying 2. So I am getting 2. Anybody else who is getting a different answer than this? So how will I number this? When I'm going to number it, I'm going to start numbering from here. 1, 2, 3, 4 and 5. Anybody has an objection in numbering? I suppose no. So at the third position I can see a methyl group. At the fourth position I can see a bromo group. Right? So I think Shanmuri, you numbered it the other way around. The functional group, the double bond will get the first priority over the prefix bromo. That is what you have done it wrong. So what it would become? 4 bromo, 3 methyl, pen 2 ene. So 1 is your right answer. Is it clear? You got it wrong. That is clear. What about the 8th one? What happens in the 8th one? 8th one, that's given CH3, CHBr, CH2OH. That is how it has been given.
2 bromopropanol 1. Second option.
No. 2 bromopropanol 1. Okay. Anyways, this option is also written wrongly. It should be 2 bromo 1 propanol or propan 1 ol, right? It has been misprinted. This option should be like this, right? This option is misprinted. This one should have been here, like this. Right? So how did I numbered it? I numbered it from here 1, 2, 3 and I got at the second position bromo group. It's a 3-member carbon chain, propan 1 ol. Clear? What about the 9th one?
Ethanol.
Okay. Ethanol. Anybody else? Reshma is also saying ethanol. So, had it been instead of IUPAC name, common name, then what would have been the answer? If instead of IUPAC name, I would have asked the common name of CH3, CHO would be? Option 1, you are answering for this, right, Shanmuga? The common name?
Acetaldehyde.
Yes, acetaldehyde, right. So the IUPAC name is ethanol and acetaldehyde is common name. Clear? Let's see what else do I have. So I have 4 examples. Tenth, 11th, 12th and 13th. Quickly solve them. Tenth one, acetyl salicylic acid. That's the common name. What is the source of acetyl salicylic acid in nature? What is the source of it? Where do you find acetyl salicylic acid in nature? In nature as in like, where is it actually commonly used?
Aspirin.
Aspirin, right. The medicine which you generally take for a headache or even for a pain. Aspirin. So its composition of aspirin is acetyl salicylic acid. How is the structure looks like? Structure of
Second.
Okay, let's see. So that means COOH with OCH3 or it is OCOCH3. How it is?
OCOCH3.
Yes, OCOCH3. That's why it is 2-acetoxy-benzoic acid. Clear? What about the 11th one? Which functional group is this? Which functional?
Ether.
Ether. This is ether. So when I have to name an ether, how do I name that? I need to select the shortest chain as prefix and the longest chain as word root. So the shorter chain would be the CH3 and the longest chain would be C2H5. So that means this becomes methoxy.
Second option.
Yes, methoxyethane. Clear? What about this? IUPAC name of CH3C triple bond N.
Ethane nitrile.
Ethane nitrile. And the common name would be? What would be the common name?
Acetonitrile.
Acetonitrile. It's the most versatile solvent. Many organic compound is carried out in acetonitrile. It's the most versatile solvent. Okay. This is your common name. IUPAC name of this. What is this group?
Ester group.
Ester. Not Easter, Ester. ESTER. Easter is a festival. Right? Yes. Ester group. How do I name this? Ester? Okay. 1. Ethyl acetate. Okay. Shanmuga.
Ethyl ethanoid.
Yes. IUPAC name has been asked. Ethyl acetate is its common name. So what is the IUPAC name? Ethyl ethanoate. Okay? Sheetal and Shanmuga? Fine. Proceeding further. So let's say I have given you name this compound. IUPAC name. How do I name this?
Ma'am, one phenyl butane.
1-phenyl butane here.
Ma'am, propane.
Propane.
Ma'am, propane. Sorry, ma'am,
Propane. Everybody is agreeing with this. Why did he do that? This group is basically benzene with one less hydrogen, C6H5. When it is considered as substituent prefix, then it is referred by the name phenyl. So if I am going to number my carbon chain from here, what does it becomes? It becomes from the 1 position the phenyl group is attached. So 1-phenyl propane. Clear? Kindly name this compound. Somebody said something?
Bromo 4,4-dichloroheptane.
Okay, you said what? 3-bromo
4
dichloro.
dichloro.
And what is the longest chain? 1, 2, 3, 4, 5, 6,
Heptane.
7. Heptane. Clear? I'll start my numbering from here. Third one. Third one, how would you name the third one?
Ma'am, 3 oxo butanoic acid.
3-oxo-butanoic acid. Everybody is able to understand how are we doing it? So number of carbon total 1, 2, 3, 4. So that's why the word root became but. And at the third position, when I compare carboxylic acid and carbonyl ketone, which group gets the first priority? Carboxylic acid. That's why the numbering starts from here. 1, 2, 3. At third position, I have a carbonyl group which is represented as oxo. So 3-oxo-butanoic acid. What about the fourth one? Fourth one.
5-butane non-2-on.
5-butane. Ankit, can you type that please? Rest of you, please also type your answer. Okay, Ankit, the first mistake, 5-butane. How can that be 5-butane? You tell me that. It can be either butyl, because when it comes as a prefix, it cannot be a full name, right? It is one hydrogen
Yes, ma'am.
less, so then it becomes butyl. And so what does it become? So which one is your longest chain? Anybody else who wish to
Ma'am,
attempt
9
this?
carbon.
Who wish to attempt this? Let's see what everybody else is also saying. So 1, 2, 3, 1, 2, 3, 4, 5. After this I have 2 routes to go. 6, 7, 8, 9, 10. 6, 7, 8, 9. So see, I'll go this way. How come the 9 carbon? It is 10 carbon is the longest chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Everybody is getting no name. It's not no name, it's decane. So 1, 2, 3, 4. So 5 butyl. After that, at second position, I have a carbonyl group. That means decane 2-on. Right? Is it okay now?
Yes, ma'am.
So you should be ensuring whether what is the longest chain you are getting, right? So let's see based on that. One more. how will you name this compound?
2,4,6 trimethyl phenol.
Everybody agrees? So phenol will get the first priority 1, 2, 3, 4, 5, 6. That means 2 position, 4 position and your 6th position, trimethyl. Trimethyl phenol. Phenol why? Benzene ring with the OH group will be considered as phenol, right? Can you name this 6th? What will be the name of this compound?
Ma'am, 7-chloro-7-hydroxy of 5-4-one.
Okay, so you are saying 7-chloro chloro 7-hydroxy. After that what did you say?
Oct 5-4-one.
Oct 5N4-one. Perfect. So that means I'll start numbering from here. 1, 2, 3, 4, 5, 6, 7 and 8. Why is it happening? Are you also getting the same type of screen which I am getting? The numbers are getting. Sorry, the screen was causing some trouble. You are able to see it, right?
Yes, ma'am.
So in this, why it is being incorporated inside the name? Because it is a primary suffix, right? Now based on this, you will get n number of questions for practice in the IUPAC nomenclature. So we will proceed further from here to isomerism. So isomerism, what is the word suggest? What is isomerism? Isomerism is something that it has same chemical formula or molecular formula is same, but due to the arrangement of the molecule, it is structurally or it is spatially different, right? Same chemical formula, different structural formula. That is how I can put same molecular formula, different structural formula. If I have to define what is actually isomerism is. So isomerism is being broadly classified into two categories. What are the two categories? Structural isomerism, stereoisomerism. Structural isomerism is what? Same molecular formula but different structural formula. Whereas in stereoisomerism, same molecular formula but the atoms occupy different position in space. That means when I see a 3D structure of that molecule, then the attachment of the group in the 3D space is different, right? So these are the two. So that means structural isomerism is basically there is a bond breakage and the new bond making. So if I have to convert one structure from one to another, there has to be a bond breaking and bond making process. But in the case of stereoisomerism, the bond connectivities are same. There is no change in the bond connectivity, but the arrangement in the space is different, which is making it different molecule, right? This much is clear. The further structural isomerism has been broadly classified into three categories, but there are two more categories as well. But for the time being, let's try to understand these three categories. Chain isomerism. What is chain isomerism? What is chain isomerism? Anyone who can tell me what is chain isomerism is?
Same formula but different carbon skeleton system.
So that means if at all I have a molecule of a 4 carbon, if at all they are connected in a linear manner, one after one after one after another, this also has C4H10 as its molecular formula, and when I break one of that CC bond and connect it to the second carbon, this is also C4H10. But what is the difference? The connectivity is different. So in the chain, this was a straight chain. Now there is branching, right? That is what I meant by chain isomerism. So I can have iso, I can have neo, I can have straight chain N-butane, isobutane, right? I can have that. Position isomerism. How is position isomerism defined? How is the position isomerism defined? So in this case, I can say the functional group. In this case, what can I say? The functional group. Presence of the functional group at different positions. So let's say if this green is your Br molecule. In the first molecule, it is connected to the carbon number 1, whereas in the second molecule, it is connected to carbon number 2. So position isomerism. So that is the position of the functional group is different, but the molecular formula is same. What about the functional group isomerism? What is functional group isomerism?
Ma'am, same formula but different functional group.
Yes, same formula but different functional group. So if you see, if I consider this orange ball to be my oxygen, here the bond is, the functional group is alcohol, whereas here it is ether, right? I can even have carbonyl group, aldehyde and ketone as an example for this. So that means structural isomerism has been broadly classified as chain isomerism, position isomerism and functional isomerism. So when I get a question in my competitive exam, what do I get? Let's say I've been given CH3, CH2, CH2OH. What type of isomerism will this molecule show? That is my question. In that case, what will be the answer for it? If I have been given, let's say CH3, CH2, CH2OH, which type of isomerism will be shown? I have been given 4 options: chain isomerism, position isomerism, functional isomerism, functional group isomerism, and none of these. What would be the answer for this? What will be the answer? CH3, CH2, CH2OH. Can it have more than one answer?
Yes, ma'am.
Yes, it can have more than one answer. What will be the more than one answer?
B and C.
Yes, it can show position as well as functional group. If I see position isomerism, CH3, CH2, CH2OH at one position, it can have a branching at the second. So this is my position isomerism. On the contrary, if I see them as functional group, CH3, CH2, CH2OH, which is an alcohol, which can be converted into ether by flanking oxygen in between the methyl chain, right? So it can have 2 answers. Clear? So I told you there are 2 more isomerism which is present in the, what are they? In the structural isomerism. Have you heard about metamerism? Have you heard about metamerism? What is metamerism?
Different alkyl groups on different side of functional group.
Yes. So this, first of all, what I am trying to understand, this has a very limited application. This has very limited application. Why does it have very limited application? Because of the fact that it can only be shown by ethers or probably sulfur flanked group. So if I see it, CH3, CH2, O, CH2, CH3. So in this case, 2 carbon on either side. I can have CH3, CH2, CH2, O, CH3. So in one side there are 3 carbon, in the other side there is 1. And when I say it has limited application, because it is applied only to very few of the molecule. So I can have similar example with the sulfur group as well. Right? So this type of isomerism contains different alkyl chain around a functional group. Right?
Yes, ma'am.
Sorry.
Ma'am, it can be shown by ketones also.
Yes, that's what I was coming at. So you know the number around the ketone molecule can also vary. So when by definition of this molecule, this isomerism, it is number of alkyl chain around a functional group. So I can have this also as an example. What would be the name of this and what would be the name of this? What will be the name of each one of them?
Pentane 3-on.
Pentane 3-on and the other one?
Pentane 2-on.
So pentane 3-on and pentane 2-on. Perfect. What is the fifth type of isomerism which is possible? Tautomerism. Now what is tautomerism? Have you heard about tautomerism?
Yes, ma'am. Keto-enol tautomerism.
Keto-enol tautomerism. So that I know. Keto-enol is the example for it. What exactly is happening between keto and enol? If I try to understand it, what exactly is happening? Keto, that means I have something like this, right? I have something like this. This is my keto. And enol means what? That this hydrogen has shifted. So when this hydrogen has shifted, that means it has become OH over here. So this is my enol form and this is my keto form. And this is the tautomerism which I am having. So what do you actually, if I have to define tautomerism, how will I define it? So what are they differing from? Position of a proton and position of electrons. So I can say the isomers which differ in the position of a proton and electrons. Right? I can say that as a definition for tautomerism. Yes? Everybody agrees?
Yes, ma'am.
So, next type of, so these were the structural isomerism. Now we come to stereoisomerism. Stereoisomerism as defined over here, different spatial arrangement. In that category I have two different isomerism, geometrical isomerism and optical isomerism. When I talk about geometrical isomerism can exist only in double bonded compound, that is compounds having double bond, that is alkene molecule. And how is that possible? They differ in the groups present around that double bond. So if at all both the group, the same type of group is present on the same side of the double bond, then it is cis. If they are present oppositively, then it is trans. This is my cis molecule and this is my trans molecule, right? Similarly, optical isomerism. Optical isomerism, what happens in this is that if I have a carbon chain attached to 4 different groups, if I have carbon chain attached to 4 different groups, that means tetrahedrally bonded carbon atom which is bonded to 4 different groups. If I take the mirror image of that compound, the mirror image and the compound both are different. How are they different? They are not different in their chemical properties, they are different in their physical properties, especially towards the plane polarized light. So, the experiment which is referred by the name polarimeter is used to see. So, you know, light has planes in all the directions, and when it's passed through the polarizing filter, then I get plane polarized light. This experiment everybody remembers what it is? So what exactly is happening is, I have a lamp which is a source of a light which has oscillation in all the angles, which I am making it pass through a polarizing filter, which results in a wave which has oscillation in only one plane. That's why it is referred as plane polarized light. This plane polarized light, when passed through the sample, so in the C there is a sample which is being kept over here. The sample, when it passed through the sample, an optically active compound, so that means an optical isomer, will change the angle by theta degree, and this theta degree change can be observed with the help of analyzer. So, what am I trying to say? Optical isomers are those isomers which change the angle of the plane polarized light. Can I say that?
Yes, ma'am.
So that means what I am trying to say? I am trying to say those two mirror images which I have for a compound. So let's just see these two compounds. These two compounds only differ in their spatial arrangement when they are non-superimposable mirror images. So how do I define it? So my hand, if I take my hand and if I take the mirror image of my hand, this will be my mirror image of my hand, right? And when I try to superimpose it, can I see that the thumb is coming on the opposite side and all the fingers are on the different side? So that means my hand is an example of a non-superimposable images. Yes? No?
Yes, ma'am.
So that means what exactly is happening? These non-superimposable images are referred as optically active. What is optically active? Optically active are those compounds which can change the angle of plane polarized light. Now, I have to see, like if at all I have these two molecules. So if at all this molecule rotates the plane polarized light by plus 36 degree, and if I change the sample to sample B, this one, then what the value observed in this case won't be plus 36 degree. 36 degree, but instead it would be minus 36 degree. That is, they rotate the plane polarized light up to the same extent but in the opposite angle. So what is the relationship drawn in the plane polarized light? Optical isomers are going to have same chemical property, same physical property. Where do they differ in? They differ only in the place when they turn the plane polarized light angle. Is it clear? Is it clear?
Yes, ma'am.
Shall I repeat it? Fine. So, what can I say about optical isomers? What is the first thing I know? They are non-superimposable mirror images of each other. What are superimposable mirror images? What are superimposable mirror images then? What are superimposable mirror images? Ball. If I have a football, any ball for that matter. So let's say if I have a ball and I take the mirror image of it, right? And when I try to superimpose it, is it superimposable? Yes, no?
Yes, ma'am.
It is superimposed. So they are optically inactive in nature because they are superimposable with one another. What is the key feature of an optical isomer? They are non-superimposable mirror images of each other. So you cannot stack them one over the other, right? So I know optical isomers, so that means there is some one particular thing which is making it important what it is, that is they differ only in their reaction to plane polarized light, nothing else. And the one which turns to the right is referred as dextrorotatory and the one which turns to the left is referred as levorotatory. Dextrorotatory also represented by a small d or a plus sign, whereas levorotatory represented by small l or a minus sign, right? What say if at all I fill the sample with the 50% of each isomer, 50% of the D isomer and 50% of the L isomer, what would happen in that case? What will happen to the plane polarized?
No optical activation.
No, so that's not the activation. So you should say it will lead to no change in the angle of plane polarized light, or else the mixture behaves as optically inactive because the effect, what effect? The rotation caused by one is nullified by the other. This type of mixture is referred as racemic mixture. Clear? And due to this activity, many of the drugs which exist in nature, only one form is active. It has the main application in the medicinal drug industry. So if I think about it, so I know my body consists of glucose molecule. Can I say? My body consists of glucose molecule.
Ma'am.
So in nature, every glucose or every sugar moiety known in the world, natural occurring, is D form, the capital D form, and D and L form, right? Those are the two forms. So the L form doesn't exist in nature. And if I will consume, so like L form can be synthesized man-made, and if I consume my L sugar, it cannot be metabolized, that is, it cannot be broken down to CO2 and water, because the enzymes which helps in the breakage of glucose cannot determine what L sugar is. It can only identify D sugar. You know, enzyme work as lock and key mechanism. When they work as a lock and key mechanism, only the D isomer can interact, not L isomers. Making sense?
Yes, ma'am.
So what exactly is happening? Why are they most important? They are most important in the drug industry. And this phenomena of optical isomerism arise from the fact chirality. Have you heard about this term, chiral?
Yes, ma'am.
What is a chiral?
Ma'am, all four bonds of a carbon are with different things.
So that means a chiral center. You're talking about chiral center? That is what you're talking about. Chiral center is the center at which the all groups attached to that are different. So if I have an example, so CH3, C2H5, H and Cl. Is this center chiral in nature?
Yes, ma'am.
How do I identify a chiral center? That chiral center should have 4 different groups attached to it, right? So the chiral center is represented by a star. So that means this compound is optically active when it is non-superimposable on its mirror image. When I take the mirror image of this compound, what do I get? C2H5, CH3, and then after that, what would happen? The above bond becomes the below and the below bond becomes above. So you know this is above the plane and this dash dash 1 is the below the plane. So in this case, below the plane was hydrogen and above the plane was Cl. When I took the mirror image of it, the plane bond just shifted to the 180 degree, and what happened to the above and below? The above becomes the below and the below becomes the above bond, right? So this is optically active in nature. So what kind of questions are expected? How many chiral centers are present in one molecule? So let's say, if at all, a question is given to you like this: CH3, CH3, CH, Cl, CH2, CH, Br, CH2, CH3. How many chiral centers are present in this molecule? If this is your question, what will be your answer?
Ma'am, 2.
What about rest of you? You've been quiet from quite a long time. Okay, it will be 2. Which one? Can you name this compound first for me? What will be the name of this compound? Which way will I be numbering? Left to right or right to left?
Ma'am, from where fluorine will come first?
1, 2, 3, 4, 5, 6. So that means my name becomes 4
4 bromo,
Yes.
2 chlorohexane.
4 bromo, 2 chlorohexane. Okay, so that means what are my chiral center? Carbon number 2 and carbon number 4. So in your options they could have given it like this. So carbon 5 and carbon 6, or else carbon 4 with carbon 1, or else carbon 2 with carbon 6. So in this I should know the correct way of numbering it first, and then only I can select the option, because if I do not number the compound correctly and label it correctly, this options I won't be able to select it, right? So the numbering becomes most important for identifying even the chiral center. Clear?
Yes, ma'am.
Now, this is the one type of example which could actually be asked, how many stereogenic centers are there. There is another very common question which is always asked, like how many pi bonds and sigma bonds are present. So let's say if I give you an example, CH2 C double bond O, and it's asking how many sigma and pi bonds are present. What will you answer? What will you answer? How many sigma and pi bonds are present?
Four sigma, 1 pi.
4 sigma and 1 pi. So can I have the differentiation? What all sigmas I have? What all sigmas? So if I open the structure, it would be like this. So there has to be 1 more hydrogen in order to satisfy the valency, right? This will be it. So if I calculate the number of, so sigma CH bond, how many of them are present?
Four.
4. Sigma CC bond, how many of them are present?
1.
1. Sigma CO bond, how many of them are present?
1.
And sigma, pi CO bond, how many of them? 1. Right? So it has 6 sigma and 1 pi as a total if I wanted, or if I have been asked in a breakup form, then what is the hybridization of each carbon over here? Hybridization of each carbon.
sp3 and sp2.
sp3 and sp2, right? So let's say I give you another example. Draw all the possible structures and name them for C6H14. I want you to draw all the structures and name them. What all will be the IUPAC name? What will be the how many isomers are possible? What is the type of isomerism this will be showing?
Chain isomerism.
Chain isomerism it will be showing. Perfect. How many isomers are possible and what all the names of those isomers will be? Chain isomerism. So that means one chain would be CH3, CH2, 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 CH3. That means 1, 2, 3, 4, 5, 6. Then that is hexane. Right? Another one I can have CH3, CH2. Let's say I have CH3 branching here, CH2.
Ma'am, 7 isomers.
7 isomers. Okay, everybody is getting 7. Okay, Shanmuga and Sheetal are saying 5 only. Ankit, can you tell me how there will be 7 not 5? Can you tell them how? So this will be...
Ma'am, 2-methyl pentane.
3-methyl pentane, then after that
1,4-dimethyl butane.
3-methyl, 2-methyl pentane, then after that you are saying what?
1,4-dimethyl butane.
1,4-dibutyl. No, one, if at all you are considering one position, it cannot arise. So 1, 2, 3, these 3 you are certain about it. Let's see how the branching will start. So let's say I have 4 and 2 are, so this becomes 2,3-dimethyl, 2,3-dimethyl butane. This is my 4th one. What will be the 5th one? 5th one could be
2,2-dimethyl.
So let's say if I have 2,2-dimethyl, how 2,2-dimethyl? Yes, so like this you are saying, right? CH2, CH3, right? 2,2-dimethyl butane. So you got 7 of them. What more? 1, 2, 3, 4, 5. I got 5. Reshma is also getting 7. Which one did you get after this? Apart from these 5, what is your answer, Reshma? Ankit, you can also tell me. Apart from this, what else did you get? Sheetal and Shanmuga, did you got all these 5 or different than this? Hexane, 3-methyl pentane, 2-methyl pentane. Perfect. 2,3-dimethyl butane, 2,2-dimethyl butane. Can I have this as well? 2-ethyl butane. Will I be able to have this? Ethyl butane. It's not possible?
No, ma'am.
Yes, it is not possible because then you will be considering the longest chain as the wrong one. So this is not possible. So who else is getting more than 5? Tell me which one you are getting. Tell me Ankit. Tell me Reshma.
Ma'am, I did wrong. I wrote 1-methyl pentane.
Yes.
Ma'am, but that is normal hexane.
Yes, that is normal hexane. So 5 isomers are possible in the case of C6H14. Clear?
Yes, ma'am.
Fine. So similarly, let's say if I have been given to you NO2 CH2 CH2O minus and CH3 CH2O minus, and I ask you which one is more stable and why. Which one is more stable and why?
Ma'am, first one.
First one is more stable. Why?
Ma'am, because NO2 is electron withdrawing group and O negative is already having a lot of electron.
Okay.
But ma'am, CH3, CH2 is the electron donating group.
So
So it
what
will
is the
destabilize O
effect?
negative.
What is the effect referred as? We studied 4 different effects, right? Resonance effect, inductive effect, electromeric effect, and mesomeric effect, hyperconjugation. We studied all this. What effect will be shown over here? Due to which you are saying my A compound is more stable than my B compound. That is what you are saying, right? A has more stability over B. When A has more stability over B, why? You are saying the electron density and everything. What is the effect referred as? Which effect makes this compound more stable?
Minus I effect of NO2.
Yes. So, minus I or inductive effect, the inductive effect of NO2 aids the distribution or aids the pull of negative charge on oxygen, negative charge on oxygen to distribute, resulting in more stability, right? So if at all 4 effects are given to you, what you will say? Inductive effect, resonance effect, or mesomeric effect, or hyperconjugation. What would be your answer? Inductive effect. Clear?
Yes.
Fine. Let's say if I have been given, let's say I need to show this CH3 COOH plus OH minus, resulting in CH3 COO minus plus water.
Can you wait outside? Is it possible?
So the question over here is identify the reagent. What type of reagent is this and what kind of reaction is occurring over here? And what is the electrophile or nucleophile over here? So you have studied about electrophile and nucleophile, remember? When you studied about it,
Nucleophile.
it is a nucleophile. Everybody is clear about it? This reaction is governed by a nucleophile which is present as OH minus over here. Clear? Everybody is clear about it?
Yes, ma'am.
Okay, let's have one more example for it. C6H5 plus CH3CO plus. This molecule is bold and it is resulting in formation of C6H6 here, C6H5 COCH3. So what is this over here? What reagent is causing this thing to happen?
Electrophile.
Electrophile. So this is an electrophile. Clear? So let's say I have been given a molecule CH3, Cl, Cl, CH3. What type of isomerism does it shows, and what is the isomer known as? What type of isomerism is this compound showing, and what is the isomer referred as?
Geometrical isomerism is shown.
Yes.
Cis and trans are the isomers.
Cis and the no. So which type of isomer is this?
Stereoisomerism.
Geometrical isomerism, that is fine. It shows geometrical. And you said cis or trans will be showing. Which isomer is this? Cis or trans?
Trans. No ma'am, cis.
It is a cis isomer. So let's say instead of one CH3, I have, and here also. So let's say I have Br and I have here let's say C2H5. Is there any way of classifying these type of compound when all the four groups present on the molecule are different? Is there a way? There is a way to do that? In geometrical isomerism, I studied about cis-trans. Remember? If at all, instead of a cis-trans, I know two groups should be present in order to define it. So just like the previous one. Instead of that, if I have this molecule, can I say something about the isomer which will be present around the double bond? Double bond shows cis-trans isomerism. Is there any other type of trans isomerism which is shown? That is referred by the name JEE-isomer. Have you heard about them? Have you heard about them?
No ma'am.
So, the JE-isomer, Z is a German word which means together. Okay. And E is also a German word which means apart. So, what is it trying to say is, the Z isomer is analogous to your cis isomer. How it is analogous to cis isomer? In the cis isomer, what happens? Both the groups present on the one side is same, right? That is how it is. If at all I consider this example, CH3, H and H, right? But in this case, I cannot have the similar situation. For that, what I will do is, I will add the priority. What is the priority? I'll see the bond with the atomic masses. So if I see this bromine and chlorine, which one would have higher atomic mass? Which one would have higher atomic mass? Bromine or chlorine?
Bromine.
So this is my first priority, and this becomes the second priority on this side. Similarly, here CH3, C2H5. So I see the bond connectivity. Here the carbon is connected to 3 more hydrogen, whereas here the carbon is connected to another carbon and 2 hydrogen. So that means this becomes higher in priority in comparison to this. Can I say that? Yes, no, doubt? What I am trying to say is, if at all, so you can see C2H5, that means it is C H2, then CH3. So that means this carbon is attached to another carbon. Here the carbon alone is attached to 3 hydrogen. Both the 3 hydrogens have low atomic masses, but here the carbon 12 is attached to another carbon 12 as well as to 2 hydrogen. So it becomes higher in priority. Yes, no?
Yes, ma'am.
So when it becomes, so I can see priority group 1, priority group 2, priority group 1, priority group 2. So the 1, 1 are lying apart from each other. This becomes my E isomer. Just like cis-trans, the groups were similar. So what happens in cis-trans? So CH3, CH3, H, H. If I have to do this, so let's say H and CH3. This is second priority, this is your first priority. Similarly, this is your second priority and this is your first priority. First priorities are lying apart at the opposite side. So this becomes your E isomer. And this becomes your Z isomer. Because in this, the same priority groups are lying on the same side. Making sense? No? Or is it too much? Let's do one more example. It will become clear. Let's take this example. F, H, Br, H. F, H, Br, H. You have to classify them as Z and E isomer. When you have to classify them as Z and E isomer, what would you do? How would you do it? What should be my first step? Prioritizing. So when I am doing the priority, I will be doing on the each side. So when I see H and Br, which one would be high priority? Bromine would be high priority. Hydrogen will have the low priority. Similarly, fluorine and hydrogen. Fluorine will have first priority. Hydrogen will have the second priority. Is it making sense? Yes, no? So when I can see the same priority groups are lying on the same side, then this becomes my Z isomer. On the contrary, if I see over here, this is my first priorities and this is my second priorities, they are lying opposite to each other, this becomes my E isomer. Clear? So, as you know, cis-trans was limited only to the group should be same. That is why Z and E isomers also came into the picture. What if the groups are different? It's not necessarily that every time the groups will be same, right? It can be different as well. So when it is different, the geometrical isomers now has been divided into two parts. Cis-trans isomerism, ZE isomerism. What say? Making sense? I think the class got confused, or what happened? I'm not getting a response. Otherwise, type in your answer. Ma'am, my mic is not working. Oh, okay. No worries. Try joining in again otherwise. So is it understood? Z and E isomers. Even these questions do arise. Find out which isomer, Z isomer or E isomer. The compound is given to you and you have to find out whether it's a Z isomer or an E isomer when all the 4 groups attached are different. Fine. Practice some more questions on this. Okay. And I think next class onwards, Vishu sir is going to continue with your physical chemistry. Okay. And I'll be seeing you next whenever we get to meet each other. Fine?
Yes, ma'am.
Okay. So I shall stop here today. I will see you in the next class. Thank you.